let's write the points which we were discussing. So we understood that the convolutional layer basically operates on the convolutional filters, and they are applied onto the input image to produce the feature maps. That's fine for us. And the features that are extracted from the convolution layer are determined by the trained convolutional filters. They are also fine for us. These points we already have written. Now let's proceed further. So therefore, from this particular example, what I understand is this. The features that the convolution layer extracts are going to vary depending upon what type of convolution filter has been used. Okay, depending on which type of the convolutional layer, or I can actually specifically I should write filter, which specific type of filter, I'll put the layer in bracket. Okay, which type of the convolution filter has been used. It depends on that. So the feature map that the convolution filter creates is processed through the activation function before this particular layer provides you an output. So even there is an activation function, right? So I'll write that point as well. The feature, map that the convolution filter creates is processed through the activation function before this particular layer, that is a convolutional layer, provides the output. So the activation function of this convolutional layer is identical to that of any ordinary neural network. Okay, so any function that we use can be used here, but specifically the ReLU is the most preferred one in the recent applications. Okay, but definitely the other functions like sigmoid, tan hyperbolic, any other functions which we have seen earlier, right, can also be used here. Okay, so activation functions also, anyway, we have seen that they are dependent on what exactly we are trying to perform, what type of algorithm we are trying to write, depends on that. So overall definitely depends on, right, those points. Okay, let me write that. So the activation function of the convolution layer is pretty much identical to that of the ordinary neural networks, to that of simple neural network, that is ANN. Okay, now in ANN I have seen many of the activation functions. Which one you prefer, right? So the ReLU is most widely used, right? So in the recent applications, okay, the rectified linear unit, ReLU, is widely used, right? Uh, but definitely others are also can be used, but others activation functions such as, right, the one very common one we saw several times is a sigmoid, okay, such as sigmoid. Even we have used the tan hyperbolic, right? Tan h function can also be used. All right, let's move further. Now after the convolution layer, we have another layer which is to the next immediate right side of the convolutional filter, which is, sorry, convolutional layer. That layer we have never considered, and now we are going to look at that particular layer, and that layer is called the pooling. It's the pooling layer, right? We have seen that pooling layer is used to reduce the size of the image, as it's going to combine the neighboring pixels of certain area of the image into a single representative value, right? So we already have defined this, right? Let me write the working of pooling layer. Okay, so here the pooling layer, it is used to reduce, I can write reduces the original size, okay, of the image, in the sense whichever the output of the convolution layer is given to the pooling layer. So pooling layer will further reduce the output of the convolution layer, right? So output of the convolution layer itself is an image, right? It's a feature map. We are trying to reduce the feature map further. Okay, so how we are going to do that, we'll see. So it further reduces the size of, I can write size of the image. So as it combines the neighboring pixels, neighboring neighboring pixels of a certain area of the image into a single representative value, into a single, it gets converted into a single value. It represents all those pixels in that area, so that we'll write it as a representative value, single Okay, so that's what is a pooling. So normally the pooling is a very typical technique. Many, not just this particular technique of convolution layer, not just a convolution neural network, but also many other image processing schemes are already employing. Okay, so I can write that because as the CNNs are originally developed to process the images, so they brought the concept of pooling over there, but now it's going to be used in each and every field. Okay, so I can write one point about it. The concept of pooling is used in all the image processing schemes, right? It's widely used now. So in order to conduct the operations inside the pooling layer, we should determine how to select the pooling pixels from the original image and how to set the representative value of each of them. That's what is a very important piece, because once you decide that, you can go ahead and perform the pooling. So in order to conduct the operations inside the pooling layer, so what we need to do, right? First, we should decide. First, we should determine the way to select, that is, how to select the pooling pixels. How to select the pooling pixels from the image. That's the first question. And the next point is that how to set the representative value. This is the question. Okay, how to do that. Now, normally you see that how many pixels should be selected, we can anyway we can say that we can set it random, but how to set the representative value? If the values of these pixels are low, set a high value, right? Or if they are high, set a low value. You can put a inverse relationship, you can put a linear relationship, you can put a non-linear relationship, etc. Varieties of options you have to set the representative value. So how to do that, we'll see that. Okay, now if I consider a specific pixel, right, the neighboring pixels are usually selected in the form of a square matrix. That's obvious, we already have seen that, like 3 into 3, 5 into 5, 7 into 7, etc. Okay, uh, and the number of pixels that are combined will definitely differ from a given problem to the next problem, obviously, right? And the representative values are usually set as either mean or maximum or minimum and so on. Many options we have. Okay, so let me write that point. So the next point is this. The neighboring pixels the neighboring pixels are usually selected are usually selected from one from a square matrix. Right. So normally that will be the standard procedure, but the size is going to vary. Right. I'll write size varies from problem to problem. It's going to vary. Obvious. Then the representative value, right? How to represent the value? That was our next question, right? So we'll answer that now. The representative value can be set as the mean or max or minimum of them, etc. Okay, of those selected pixels. Okay, now let's look at one example, right? Though it looks like a very complicated process, right? The operation of the pooling layer is very simple, right? We have a two-dimensional matrix with us. It's an image, right? You have to consider a specific size of the image and consider a specific region out of that, right? Without any overlapping. Whatever region you are trying to concentrate or whatever region of your image you are going to consider, simply apply the pooling layer, right? So pooling layer, when you apply, right, the result will be of a smaller size, right? I'll show you the operation here. So this is the example of the pooling operation. So consider the image I is equal to, I'll consider the same image 1 1 1 3 4 6 4 8 30 0 1 5 0 2 2 4. This is the image. So let's consider two different examples of pooling. First example, I want to perform the mean pooling. So remember one point here, there is no question of overlapping. In the sense, if I consider, uh, so if I consider say 2 cross 2, right? In a sense, I have to consider each time, I have to consider a 2 cross 2 sub matrix from the image like this. I start from here. Next, note this. This is not there. It's not there. Whatever pixels are covered, it's over. You cannot consider the same pixel again. My next position has to be like this because no overlap. Very important. Without overlapping, you have to. So without overlapping, you have to apply this. Is it? The fundamental idea of pooling is that there is no question of overlapping. Once a pixel is covered in one pooling operation, that pixel should not be covered once again in any other pooling operation of the same image in the same stage. For example, I'm considering a 2 cross 2, right, is the pooling size. So 2 cross 2 is 1 1 1146. This 1146 cannot be overlapped with my next region like 1164. No, that is not valid because the 1 and 6 are already been covered in the previous stage. So I move on to the next polling, that is 1348. So my next polling will be like this. Okay, and the last polling will be like this. So now the idea is that the name suggests I am going to perform the mean pooling of this image, right? Which means take the sum, divide by 4. All right. So I should do 4 plus 6 plus 1 plus 1 and divide this by 4, right? So what's the answer? I'm going to get a 3 over there. Next, 1 plus 3 plus 4 plus 8 divided by 4. It's a 16 by 4, so 4. Okay, 30 plus 2, 32. 32 by 4 is 8. Then 1 plus 5 plus 2 plus 4. Once again, 12, I think. Yes, divided by 4 is 3. So the result of mean pooling is this. So I can give another example. This is very simple. The second example is the max pooling. No mathematics, no calculation at all. I'm simply going to use a 2 into 2 now. Okay, size. So that results in whatever is the highest number, you simply keep writing. All right. So I can see that the highest number that I have in the first case, that is equal to 6, right? The second is 8. Then we have 30. Then you have 4. Not 4, sorry, 5, I guess. My mistake. So the last one is 5. That's a second example. Let's go for another example. These are the options you have, right? You can even go for min pooling. It's less used, not widely used, min pooling, but still it's an example. So let's do that. So when you want to do that, so what's the minimum value in the first row? It's 1. Second is also 1. This is 0 and this is 1. All right. Okay. So like this, you can perform the polling. I can understand the point very clearly over here. Whenever I do the min, mean, max, or min, any sort of polling, the uh, result is reduced in terms of the size. Size is very less, okay, compared to the original image. All right, so that's the first one. So in a mathematical sense, pooling process is a type of convolution operation. But the difference from the normal convolutional layer, right, is that the convolutional filter is stationary and the convolutional areas do not overlap. That's the difference between the actual convolution process and this process. Okay, so let me write that point now. So in a mathematical sense, the pooling process is a type of convolution, right? But there are differences. So, but difference from the convolution layer. Compared to the convolution layer, there is difference. Okay, I can write is that. What's the difference? The difference is that the convolution filter is stationary and there is no overlap between the area, right? And I can write the convolution areas, or so overall areas do not overlap. They do not overlap. Okay. And the pooling layer compensates the titled objects to some extent. For example, let's say the pooling layer can improve the recognition of a cat which may be off center in the image, right? So something which is at the center of the image, right? Maybe you will be able to recognize even if you don't have a pooling layer. But if the object is at the corner, right, then this pooling layer is going to make it very efficient to recognize such objects. All right, this has been observed from by doing the research. All right. Uh, Again, in addition to that, the pooling process reduces the image size, right, which is highly beneficial for the computational load and also the overfitting problem, right? These two were the major issues we discussed earlier, right? So that those problems can be you can overcome those problems by just performing this. Okay, so those are the advantages. Let me write that point. The pooling layer compensates for, I can write eccentric, and also the tiled versions of, okay, uh, tiled objects up to some extent. That's the first thing, right? So, right, for example, so you by using the pooling layer, by using the pooling layer, uh, we can improve the recognition of, say, a cat, right, in the image, which is not at the center of the image, okay, which is, I can say, off center in a given image. It's not at the center, somewhere else, right? You just want to recognize that. That means the pooling layer is going to help you a lot. That's what is the application. Why do you need a pooling layer? This is the answer. If you have off-centric objects in the image and you want to classify them, definitely this is neat. Okay. Uh, and what are the other benefits? Definitely, I understand that the pooling layer reduces the size. So as soon as I say, okay, by applying the pooling layer, I'm reducing the size. So size is reduced means it's highly beneficial for us, right? Because computational load reduces, overfitting is also going to reduce. We already have seen that. Directly, we can write the point. So the pooling layer produces uh, outputs, output images of lesser lesser size keeps on reducing. Output, the pooling layer produces output images of lesser size. This implies what, right? So lesser computational load, obviously, and no overfitting. When we consider the concepts of why you need, what are the improvements you need in deep learning compared to the machine learning techniques or the simple neural networks, we considered three major problems, out of which the two problems are solved by this itself, like a lesser computational load reduces, and there's no question of overfitting as well, right? The other problem was, the error is not reaching, right, to the first few hidden layers, right? Starting from the end, error is not reaching, right? Vanishing gradient was the problem. Anyway, that was solved by whenever we implemented the ReLU activation function. So already we mentioned that ReLU is used here. So even that problem gets solved here. So the convolutional neural networks are, right, very efficient, right, in terms of the computational ease, right, the accuracy, right? Also, they are able to solve the problems, right? Major problems we face, because of which they are widely used in image processing applications.